Good afternoon, doctor. This is Lee, and my metric number is 191400. And my part is about the introduction, about the experiment 3. So for the introduction, in this experiment, you will study the inherent friction in laminar and turbulent tubes. By measuring the pressure drop and the flow rate in the pipeline, the friction factor can be estimated, and two different flow conditions, laminar and turbulent, will be studied, and the friction coefficient value obtained will also be obtained by the experiment, and it will also be compared with the established results, and the table also can be drawn in the data and analyze.
So the objective of experiment 3 is to determine experimentally the friction factor in circular pipes that have different surface roughness, and to investigate the effect of water flow rate on pipe friction factor. Next. Theoretical or fundamental background, friction losses cause pressure to decrease along the pipe, and they increase the amount of power that the pump must deliver to the fluid. Based on Reynolds number equation in circular section, the laminar or turbulent flow can be predicted if the magnitude of this dimensionless number is known. So here is the Reynolds number equation. Next is Reynolds number in circular section, which is the pipe. It is the ratio of the inertial force on an element of fluid, which is water, to the viscous force. The inertial force is developed from Newton's second law of motion, which is F equals to ma, where m is the mass and a is the acceleration. Flows having large Reynolds number, typically because of high velocity and or r, low viscosity, tend to be turbulent. Meanwhile, fluids, water, that have a low Reynolds number when it is moving at low velocity and or r have high viscosity tend to be laminar. So here, to simplify it, the Reynolds number below 2000 is laminar flow, above 4000 is turbulent flow. Between these two values is critical region. Next is Darcy's equation. Darcy's equation can be used to calculate energy loss due to friction in long straight section of round pipe for both laminar and turbulent flow. Taking note that calculation of velocity of the flow, here the velocity, the squared velocity, is for a given volume flow rate through a given pipe size requires the use of volumetric flow rate and the area, which is we know that given based on the experiment we use, we know that the diameter of the pipe is either between 1 inch or half inch for both smooth and rough pipes. So friction loss in turbulent flow. Turbulent flow is rather chaotic and is constantly varying. Tests have shown that F is dependent on the Reynolds number and the relative roughness of the pipe. That's why I explained about Reynolds number beforehand just now. The relative roughness is the ratio of the pipe diameter D to the average pipe wall roughness epsilon. The condition of the pipe surface is very much dependent on the pipe material and the method of manufacture. Because the roughness is somewhat irregular, averaging techniques are used to measure the overall roughness value. So here is the table 8.2 is the pipe roughness design value. It have different materials have different roughness. So these are only average value for new clean pipes. So some variation should be expected when conducting the experiment, because after a pipe has been in service for a long period of time.
Now I will explain the details of this procedure. Now, from in this slide, as you can see, this is the actual figure for this experiment. How the different pipes are placed and the manometer used to do. We use water as fluids. Before we started any experiments, we need to set up first. First, make sure the water supply is turned on to measure the water flow through the apparatus. Next, vent valve is open to escape the air bubbles that trap in the water flow. Next, the angle slip valve need to be closed. Also, same goes to the ball valve. For this first part of experiment, we use different diameter of pipe but same types of pipe. We compare between 1 inch of 1 inch surface, 1 inch smooth surface and half-inch smooth surface. The next, the inlet pipe of manometer is connected to inlet and outlet of the 1-inch smooth surface. The manometer readings is recorded. The difference of manometer readings is recorded. Next, with the 400 liter per hour flow rate. Next, we unplug the wire the manometer pipes and connected it to half inch of smooth surface. Then the difference of manometer reading is recorded. Then after that, the flow rates is changed with several readings to record the difference of friction factor. For the second part of the experiment, we use same pipes but different diameter. We chose rough pipes in this experiment. Then this is where the rough pipe is. Then also same the previous experiment, we record the readings and that is the pressure drops in this for the experiments.
So for the discussion for our result, for the table 1 shows that for the friction factor for different pipe sizes, by increasing the pipe diameter, the head loss is decreased and the friction factor increase. Analytically, when the inside diameter is increased, the flow rate area also increase. So the velocity will be reduced. When the velocity is reduced, the head loss there is a lower head loss due to friction in the pipe. Less energy to overcome the friction in order to meet the demands of the velocity. So for the graph 1 shows for the friction factor for different water flow rate. When the flow rate increase, the velocity of the flow rate also increase at the same rate, but for the friction factor it will be decreased at height related to the square of the velocity. So the increase in loss is very quick. Reynolds number from a physical standpoint, kinetic force overcomes viscous force. Consider the limiting cases of the zero and infinite Reynolds number. Near zero, there is no momentum and all forces are viscous. Near infinity, viscous force are negligible and momentum force governs. So friction factor will be decreased as the flow rate increase. In this experiment, for the graph 2, different water flow rate was used for the two type of pipe, rough and smooth pipe. Due to the lack of significant head loss shown when the smooth pipe was measured at 2,500 to 3,000 liter per hour. For the rough pipe, the head loss displayed when the water flow rate 400 to 2,500 liter per hour is too high and is immeasurable when using the manometer provided. So, the head loss in the two rough and the smooth pipe was measured using different flow rate to ensure that the result is measurable. Graph 2 shows that the friction factor of rough surface pipe is larger compared to the smooth surface pipe. This is because in the turbulent flow, the swirling eddies transport mass, momentum and energy to other regions of flow faster than molecular diffusion, thus greatly enhancing mass, momentum and heat transfer. As a result, the turbulent flow is associated with much higher values of friction. In addition, turbulent flow can also form a thin viscous sublayer near the pipe wall, which can be function of roughness. Generally, for the pipe with large wall roughness value, the effect of roughness is even larger as the flow rate may be function of the roughness. Consequently, roughness surface pipe with higher surface roughness will have higher friction factor. However, the viscous sublayer for smooth surface pipe is extremely small and is negligible. Therefore, the friction factor for the smooth surface pipe is relatively small. The friction factor is a minimum for a smooth pipe, but it can never be a zero due to the no-slip condition, which meant any fluid stick to any solid surface, it flows over and increase with roughness. According to Bernoulli's principle, the sum of the pressure head, the velocity head, and the elevation head is constant along a streamline. This equation is only valid in steady, frictionless, incompressible, in viscous flow, and consider all energy will conserve in such a flow. However, for a real flow in a pipe, there is an energy loss consequence of the viscous dissipation and shear stress of friction that occurs throughout the fluid in the pipe. Therefore, Bernoulli's principle of conserve of energy is not suitable to calculate the flow rate and the friction factor. The most suitable way of calculating the flow rate and the friction by using the energy equation, which is always including the friction and the loss in energy. Thank you.
And for the next part is a conclusion. For the conclusion is about the experiment was undertaken to measure the head loss in the pipe point, and due to the shear stress between the fluid and the wall of the pipe. And different flow rates were introduced along with the different diameters and roughness of the pipes. Therefore, we measure the friction factor of pipes using our measurement, and also the fluid velocity was also studied and related to the diameter, flow rate, and the roughness of the pipe during the experiment. And all in all, we chiefly studied the head losses in the pipes as long pipes of different diameters and roughness. There were few improvements required, like the forming of the bubble along the inside inlet and some leakage inlets, which will affect the value of the flow rate. With these errors taken into consideration, the experiment results would be better. So that's all my part. Thanks for listening.